Calculus is basically the math created so Isaac Newton could solve his theoretical physics homework. We use it today for a number of things like rate of change, area, and acceleration. My favorite application for these is spaceflight. Spaceflight uses calculus for many things: calculating the needed fuel, the displacement, aerodynamics, orbits, artificial gravity, effect on passengers, and many more. And I'm here to talk about a few of these and why they're so essential. The hardest part of spaceflight is getting to space. On Earth, you have to worry about the bane of all rocketry: air. This makes it costly and difficult to launch rockets. Darn air ruining everything. To escape the atmosphere, you have to make your rocket extremely aerodynamic and have an extremely efficient launch path. To do this, you have to calculate how much fuel you need to carry for the weight you have, but then you need to calculate for the weight of the fuel added, and add more fuel, then recalculate for the added fuel, then add fuel, and you get the point. So the real equation is a square root function, but you need to overestimate, and there are a few ways to do this. You could take the right Riemann sum with a period of about 1 kilogram, or you could calculate the slope at the point of the total launched weight. Put simply, you always end up with more fuel than you should when you get into orbit. Another pre-launch thing you need to check is aerodynamics. You can use calculus to mathematically describe every aspect of a craft before launch. This helps calculate coefficient of drag, which affects how much energy is lost to wind resistance. This also helps calculating orbital maneuvers, but we'll get to that later. In space, you have to be very precise about your movements. You can use calculus for many things in space, like predicting orbital change over time and calculating the best way to change your orbit. Calculus is used in physics equations as well. Some are involved in calculating simple things like velocity, and this monstrosity is used to calculate the orbital period, if it's perfectly circular. In space, there's a lot more forces acting on everything than we have to consider. To be perfectly accurate, a force chart for all the forces acting on Earth would look like this. But realistically, you only have to worry about gravitational pull and sometimes random small meteorites. In physics, calculus is required to describe these orbits with speed, time, distance, and gravitational force of the planet. But where you really need calculus is when you leave orbit. Getting to another planet takes a long time and needs very precise calculations. The delta V chart shown is for our solar system in kilometers per second. This shows the estimated delta V required to get to the planets and moons shown, though this is a simple way to show it. Say we wanted to get to Jupiter's moon Europa. You'd think from this chart that you can achieve the goals individually, but there's an easier but riskier way to do it. Since the actual path would look like this, you now might say you could go straight to Europa without worrying about the rest of the nodes. But there's an even better way to do this. Using calculus, you can calculate the air density at any given height above Jupiter. With that, you can take the vessel and find the coefficient of drag. If you use these calculations, you can calculate a path that uses Jupiter's atmosphere to slow you down enough to point you to Europa. This saves a lot of fuel and makes it easier to visit planets like Mars because it reduces wasted fuel. Now there's an important factor I haven't talked about in spaceflight, and that's people. Calculus can be used to make spaceflight more comfortable for humans. In space, you feel weightless, and that's a problem. It can be harder to eat, sleep, drink, move around, or anything we take for granted on Earth. You also lose bone mass, which can be deadly if not countered. So you can solve this by making part of the ship spin to replicate gravity. Calculus is used to find a bounce in the folds, so it feels like you're back on Earth. However, when the ship accelerates, it would feel like you're being pushed back just a little bit. And so to solve this easily, you just make the section round. You'd also use calculus to keep astronauts safe during takeoff. The body doesn't like being pushed harder than gravity, so most people can't take acceleration faster than about 10 times Earth's gravity. So you'd have to calculate a trajectory that allows for less acceleration while still getting into orbit. The reason calculus is so important in rocket science is because of the accuracy that you need to get to space. You have a slow release of energy, complex orbits, air resistance, chance, and human error to consider. Without calculus, NASA wouldn't have gotten off the ground.